Okay. Okay now. So this is basically the same problem, but we're using the graphical approach now. And for this problem, we know that the engine is accelerating. So if we create an omega versus time graph, it will look like this. We are assuming, of course, that the rate of change of omega with respect to time is constant. So that's why it's a straight vertical line going upwards, also indicating that the angular velocity is accelerating because the slope is positive. And we learned that the slope of a tangent line, of the tangent to the line, is the slope here is the angular acceleration if the graph is an omega versus time graph. And so given the standard definition of slope, rise over run, we obtain this set of values. The rise is from 1170 to 2880, and the run is from 0 to 0.21. So we plug that in and we obviously get the same answer as we did previous video. And actually this formula just looks like delta omega over delta t, and that makes sense because that formula was just the slope in a omega versus time graph. Letter B, how many revolutions, talks about angular displacement, and we know from our previous lessons that the area under the graph above the x-axis is the displacement. A little word about this: if for some reason this red line is under the x-axis or somewhere here, perhaps somewhere here, so if for some reason the values of omega are negative, you're still getting the angular displacement, you're still getting the area, and the area is right here. So instead of being above the x-axis, that area would be below the x-axis. And what I'm trying to say is, if the area is below the time or x-axis, then that displacement is negative. In this case, the area is above the x-axis, so the displacement is positive, or in the positive direction, or counterclockwise. We know that the area is just the area of the triangle here and the area of the rectangle, and substituting values still obtain the same result as we did in the previous video.